Welcome to the channel. If you're new, welcome back. If you're not new, if you're familiar with my channel. In my previous video, I showed how you can apply Google Earth Engine to monitor land degradation or land rehabilitation trends, particularly vegetation degradation or vegetation rehabilitation trends using non-parametric statistical tools such as Mann-Kendall's test and SenseSlope, which is quite often used for analyzing trend patterns for different kinds of data, whether it's climate data, meteorological data, land degradation data, cryosphere degradation data, etc. So in many tools in many domains, because it's very useful. One of the reasons why I just mentioned in previous video why it can be very useful comparing to parametric statistical tools such as regression analysis, correlation analysis. Parametric tools such as regression and correlation doesn't take into account the seasonal patterns. For instance, it's not very logical to show whether the precipitation, for instance, or temperature is increasing during the last 20 years, because it's temperature fluctuates seasonally. But when it comes to non-parametric tools such as Mann-Kendall and SenseSlope, it allows to accurately monitor this longitudinal trends, because I mentioned, if you're familiar with the theory, it is quite useful. It shows whether the general trend also increasing or decreasing. It also very close or similar in many aspects to parametric statistical tools such as regression and correlation. For instance, it has tau coefficient, analog of Pearson's correlation coefficient. It also ranges from -1 to +1, where +1 is a maximum degradation trend and maximum upward trend, and -1 is maximum downward trend, and 0 is no trend at all. And the SenseSlope shows the scope of the change. It depends on the unit you're using, and in this case we will be using this NDVI tool, NDVI index, just like before. But if previous time we used MODIS, and it's MODIS 16 image collection from Google Earth Engine datasets, which is embedded, and the NDVI is embedded to this image collection. Every 16 days MODIS measured the NDVI of a land surface and created this image collection dataset. And we just had to derive this NDVI for our study area and for our study period, and use Mann-Kendall's test and SenseSlope for our study area in Google Earth Engine. But one of the disadvantages of the previous method is that the MODIS, as you might know, has a pixel resolution as 250 meters, which is 250 multiplied to 250. It's 62,250 square meters. It is more than 6 hectares. So it's a quite large area for one pixel. Therefore, it reduces this spatial accuracy. In this video, I will show you how you can apply this Mann-Kendall's test and SenseSlope using NDVI for your study area using Landsat satellite images. In this case, Landsat 8. The reason why I didn't use previous time Landsat is because, you have to. One of the disadvantages is that you can use it for one Landsat. A Landsat 8 or Landsat 7 or Landsat 5. You can develop the code so we can combine these 3 Landsat image collections for your study area into one image collection, and then apply NDVI, and then apply non-parametric statistical tools. But it will be more sophisticated and complicated code, and it also might reduce the computational efficiency. Sometimes Google Earth Engine stacks in the moment, and also another reason why I used Modis previous time, it's because NDVI is embedded. This time we have to compute our NDVI by ourselves using this function of NDVI. So let's start. So I inserted this my study area called union. So I imported from assets. So let's say it's study area, and map center center object, this union 1, let's write it 12. So let's run. So it's quite large study area, but you can reduce it. It's up to you what study area you will use. So I will use for this larger study area for Uzbekistan, but I will particularly show you on this area 2 districts of the southern Uzbekistan. So first we'll have to upload the Landsat collection, Landsat 8 surface reflectance data. So this is Landsat 8 level 2 collection 2 tier 1, which is the surface reflectance of Landsat. So well, I can copy actually all of this, upload, just copy paste. So Landsat, so one of the advantages of this is that we have to start from 2014 as far as I remember. Well, Landsat 8, yeah, it's 2013, but I will start from 2014, and I can up to 2024, so 10 years actually, including 2014 it will be 11 years. So filter image collection filter equals to filter bounds union also so filter yeah, filter bounds, yeah, it's not equal but less than cloud cover. Uh, 20%, it's up to you what percentage you will choose. Apply scale factor, visualization. Let's add this. No, we don't have to add this. We just let's first run whether we have a problem here. Yeah, it's we already have a problem. Filter bounds filter is not a function. I think we have to. I don't need actually this one. I can delete filter bounds. Yes, this is more correct. So yeah, it's one excessive. Yeah, I think it's working. And let's continue. Now we will have to add the function named add NDVI, image, var NDVI image normalized difference, I think, yeah, normalized difference. So I open I have to use this bands, so it is SR5 band is near infrared, and SR4 is red. SR4 and return image at bands NDVI. Yes, sorry, I don't know where I stopped recording. This is the same. I just mapped this image collection dataset with NDVI, and this is the same image collection having the same image as dataset, but it has additional band at NDVI. So we added here at NDVI at bands. So now we will define years from 2014 to 2024. Let's close, and months. The same list, sequence. It's up to you which months you will define. I will start from March to October. This is a vegetation period for the study area. You have to define it for your study area, which vegetation periods you want to monitor. And now we will repeat the same steps as in previous video. Image collection from images. It's big. So we will so we have 16 days NDVIs, right? Because Landsat revisit time is 16 days, but we have to compute one image, derive one image for each month, and each pixel of this image will be the maximum NDVI of two images if there are two images for a month. But sometimes it's just one image, sometimes it's two, but we don't forget that we also applied cloud cover, so sometimes it's one image. So years, so let's start. Years map so return months map var monthly max. So we will take this image collection, filter calendar range year 1, filter filter months 1, set year. Yeah, I forgot here. We have to map. Yeah, we use function. We will have to check this. But anyway, so yes, this is year. Months. It's year. Set months. Select NDVI. Set. So before setting, by the way, we have to choose max. So yes, this is year. The same thing with months. And the last is, I just copy pasted, set. So system time start, date from year month. The image will be allocated as for the day 1, but it doesn't make sense. It doesn't make a difference because you're using you're using months regardless of a day. So what this function do, if you're familiar with the previous video, so it's so I create so yeah, I forgot to return no, sorry, yeah, it's return here, return monthly max. We have to use this flatten function here. Yeah, we don't here, it's not necessary, but anyway. So this function takes this, so I create image collection monthly, which consists of monthly max for each month and year for each month of each year from this period 2014 to 2024. That's why I mapped through years and through months. And I take from this NDVI L8 and NDVI image collection NDVI, and I took each maximum pixel, and I also set this metadata parameters. By the way, you can just print if you want to see. Print monthly max NDVI. It will just print the data collection, image collection. And the next part is to compute mean yearly NDVI from this monthly image collection. So each year has 12 months, so we computed image collection from 2014 to 2024, and consisting of 12 images, not necessarily 12, because it sometimes filter can reduce this number of images, I mean filter of cloud cover. But now we have computed the mean yearly NDVI from this monthly maximum NDVI. So I have to collect, I have to create this new image collection yearly. Image collection. It's so I will take years, the sequence I created function years. So it will be similar to the above, but the function will be shorter. So I will create var year mean. So yes, what did I do? Yes, I will use this monthly image collection. Monthly image collection. I have to filter calendar range. I will have to filter years because I'm working with years right now. Mean set return I think the function is well, so we just any case print yearly mean of NDVI and print yearly. So I took yearly. I created yearly image collection. I use years, so which I created here. Year mean, monthly, filter calendar range, mean set year. So I think it's so it computes new image collection consistent from years. I mean year means for each year, which is the average NDVI value for the whole year. So now we're moving to the most important part of the video. It's NDVI trend. So I will use this yearly reducer. Reducer Kendall's correlation. So it's embedded function. You can read it in Google Earth Engine developers. So it's developed embedded function within this Google Earth Engine platform, and now the next is tau correlation, and I will use this NDVI select it's NDVI tau. By the way, we can hear in NDVI function we can not here but here rename it as a NDVI. So now the system it better will understand. So the next is map add layer. So I just copy paste it. So I will use tau correlation. No, we just can copy the correlation clip union min -1. It's a downwarding trend, max 1 upwarding palette, and tau correlation. You can choose to change the color ramp as your own. So let's try to run it. So far, we already have this select NDVI is not defined. We can NDVI. Now let's try, because we already added. It should be the same. So Yeah, it's monthly max NDVI, 88 elements. So we can see here 88 elements for 10 years. It's 10 years, oh, actually 11 years, but let's compute it for 10 years. It's 8.8 months. So average 9 months approximately, 9 months for each year. It should took how many months? March, April, May, June, July, August, September, October. October, including, yeah, it's strange why it took 88 months year. Let's look to the monthly amounts. Bands, yeah, it's 6. So actually probably took every month 6, 7, but it's, I'm looking for 1 year, but anyway, 9, yeah, it should end with 10. So now we should hear the beginning, yeah, months. So it's actually computed for each month. So probably there is a low cloud cover during this period, and image collection, yeah, it's for 11 years. Yeah, it's correct that it's not 8.8. It's actually less than 8.8 if we will divide for 11 years, because from 2014 to 2024 it's 11 years. It will be approximately 8 months. Yeah, that's correct. So except the last year, it doesn't have any image. Strange. Anyway, so this is for this year, so we have, but for year 2024, I don't know why it doesn't have image. So anyway, let's look to the image themselves. So yeah, tau correlation should be added here. So yeah, we can see here that so this is a color ramp I use. So this red color show the degradation trend, green color show the upward trend, and this are something in the middle which shows no trend. So it's a tau close to 0. So you can choose the color, change the color ramp. So for instance, I can change it to yellow, for instance. Apply. Oh, well, yes, see that these are the degradation trends, these are the upwarding trends. So we can again I can show you that this range is from -1 to +1. So let's stretch. So I don't think it's actually from -1 to +1, it's a maximum trend. So it's actually minus 0.77. It's like correlation, minus 0.077 or -77% to 0.82, which is also, if we make analogous correlation coefficients, like plus 82%. So it's quite high correlation, so it's quite high upwarding trend. And the next is we will compute the Z-statistics. So first we will have to create the new number, which is 2024 minus 2024. So this number will be used in Z-statistics calculation of Z parameter. So if you are familiar with Z, you should remember the formula. If you don't remember the formula, or you don't familiar with Z parameter, the statistics, which is a significant test, you can look for the beginning of my previous video for Mann-Kendall. It's the same video, similar topic, but for MODIS. So I won't again use this type the formula from the beginning, so I just copy paste it. I create make mkz, so Mann-Kendall test Z, so image constant 3, multiply, yeah, I have to change tau correlation, multiply image constant n, so this is here why we use n, multiply n minus 1, square root, divide image constant n to square root rename it Z, and I will add as a layer a separate layer mk absolute numbers minimum minus 1.96. So it's Z is from minus 1.96 to plus 1.96. So it shows the statistical significance of the image. I mean, the statistical significance of the trend. So it should be this within this range. I can use clip tool here as well because it shows a very large area. Yeah, it's probably we need to use clip union 1. Yeah, it's clipped. You can use clip for computational efficiency. So let's see the legend. So you can also use the color ramp here, custom. Well, we can use palettes here. Well, it's basically not necessary, but anyways. So the parameters are computed. As well as tau correlation. This is more important for us, tau correlation, but you can use it for as Z parameter. So the next step is to compute sand slope. First, we will make some preparation for sand slope. So I will create a base year 2014. This will be used to this function as a base year to compute the normalized year. So normalized year, for instance, 2016 year is when we normalize it, we just derive from 2016 2014. It is 2, so normalized will be 2. So I will create an image collection, add year bands, and it will have the same number of images as yearly, and I will map this yearly image collection through function image, and this add year bands will have the same number of images as yearly, but at the same time it will have 2 bands. Each image will have 2 bands. First band is NDVI, so image select NDVI to float. Second is I will create now normalization of a year. I will create a variable image number, image get year. So I will derive the metadata of I will derive a year from metadata, subtract base year 2014 to float. So for instance, the normalization of year 2024 will be 10. But this is not the end. I need to create the image from this year, and this image will have the same pixel values which will contain the information about the year. For instance, each pixel will have the normalization value of a year, for instance 2 or 3 or 5. So I will create image constant here using image constant function from the year, and I will image constant this pixel value will be the year, normalized year. Rename year to float, set default projection, NDVI projection, dot update mask, NDVI mask. So it will have the same projection as NDVI here, and it will have the same mask. So it will be basically the same image, but having 2 bands. First will be NDVI. You can see it here, and year, image year will have, which will also have the metadata as year. So why I need year and NDVI, not just NDVI? The reason is that the function we will use, sand slope, needs 2 parameters. one is the independent parameter x, in this case it is a year, and second is the dependent parameter y. So according to this independent and dependent parameters, it will compute the sense slope. So I will create NDVI, and I will use now reduce reducer sense slope. Yes, so this will compute the sense slope, and now I will create the second slope, and sense select slope, and while adding as a so I will use slope clip union, so minus a minimum, no, it should be minimum 0 dot, let's say, right 0.1, and the maximum plus 0.1, and it's sense slope, and let's click OK, and let's see what we have. Clip is necessary to avoid the computational problems. So sense slope uses just as a reducer embedded function, uses two parameters, year as independent parameter x and NDVI as dependent parameter y. So this is my sense slope. I can create a palette here. Let's see what we have. So let's stretch it and see what are the values of sense slope. Yes, it's this is NDVI values. It's annual NDVI increase. So minus dot 0.13 to 0.0225. So it's not strong degradation decline and not very high decline, but NDVI is from -1 to +1. This is average annual increase or decrease. So now let's apply. So yes, this is our sense slope. We can use the inspector here to see. So this is close to neutral, I think. Yeah, it's very close to 0. This is should be positive trend of NDVI increase. Yeah, it's, and this one is degradation. So so sense slope is complementing to Mann-Kendall's test. Mann-Kendall's test shows upward and downward trend and or zero trend, and how statistical significant the trend, including the parameter. And sense slope shows the scope of the trend, which can be used how strong the degradation or how weak the degradation or how strong the rehabilitation. So export, you can export your export image to drive. I just press on Ctrl and space. So image, for instance, slope, description, slope, folder, I don't need it, but you can put, for instance, I can write GA folder, file name, I don't need this, dimension not necessary, region, union 1. If you won't put union 1, it will export the whole area, the whole Landsat tiles. So scale in this case is 30. If in the previous video it was 250, in this video, as we used Landsat satellite image, Landsat 8, it becomes 30. The pixel resolution is much higher. That's why, but the one disadvantage, you can use it for Landsat, just only one Landsat. Again, right here, Landsat. You can actually create, probably using multiple Landsats, Landsat 5 and Landsat 8. For instance, Landsat 7 has its problems, if you might know the technical problems, black lines. You can create one image collection from Landsat 5 and Landsat 8. This in here, and thus compute sensor, but you should remember that so you have to adjust for Landsat 5 and Landsat 8 the this band names. So first you will, for instance, filter Landsat 5 and then Landsat 8, and then you will create NDVI for Landsat 5, and then you will create Landsat 8, because the band names will be different. This will be in Landsat 5 SR band 4, it's near infrared, and this is band 3, red. And then you will have to combine these two image collections, combine it into one image collection. First you need to map NDVI for both images, Landsat 5 and Landsat 8, and then combine them into one, and then use this from, for instance, not 2014, it's for Landsat 8, for instance, you can use from 1990 till now, and the rest will be the same, but it will have some additional work, some additional computations and developments, but this will be more accurate comparing to MODIS, which has 250 meter square pixel resolution. So this is a more accurate spatial resolution comparing to the previous video where I used MODIS. And but at the same time it starts from 2014, whereas in previous video in image collection MODIS 16 I used it starts from 2000, so you can it has more temporal accuracy than Landsat, but I think more Landsat operates, more easier it will be, more quite often it will be used.